today. We're gonna get it. We're definitely gonna get it today. We're definitely gonna get it today. Cool. So we are, again, we're doing these stuff here. Right? So yep. Cool. It's like I've got stuck with this so many already hours that at this point I'm just like, I either get it done or I give up completely from this whole project. But what I want to, so free particles initially is to describe it a wave function, boom. So we know alpha is a real parameter. That's all we know. Compute the normalization factor n. Now, we want to, so I wanna try to do these. Again, I know this is an array, right? But I don't know what assumption has really been made here so far. By reverse engineering the answer, I know that because there's a pi here, I know that there's, you know, you're probably have to do some sort of like polar or cylindrical integration, which I've learned. So awesome. But I don't know exactly, I can't really get that exact result. So the thing is, let's see if we can, let's see if I can, first of all, let's just can we do one by one, sort of. We'll start maybe with assuming one dimension, and then get the actual function like properly done. So okay, so what do we have? So this is the function that we have. I'm not gonna assume this is real because we don't know. Maybe, yeah, maybe we can. I don't know. I know we know alpha. So, but hey, alpha is a real parameter. So alpha can, you know, we can. That's the thing, right? So alpha could also be negative, and then so this exponential decay is not like, yeah. It could be negative, right? So let's try to understand first what is the function that we're plotting, that we're working with. So shall so this is the function that we're plotting, okay? So this is the function here. So this is what we've got to do. And the thing is, I know these the n thing we can definitely take off the integral. So we're really just I think so, right? I mean, so it's just a constant, right? I think that always applies. Integral identities. Do we have anything that I can? So integral I think that is something we can. The integral of a constant times a function is the constant times the integral of the function. So happy with these. This means let's just get rid of these for now. Like for the sake of simplicity, let's just leave the n times the conjugate of n side. So really, really all that we're doing is these, right? So, okay. It's maybe not the best to do it like that. I should just kind of maybe work with these expression of like S11 and then just do basically what the result is telling me to do here. So -2 times these. So let's just work with these. No, so let's just work with these. So this is the function that we have, e to the power of -2, and we know yeah, you know, that's something we don't know. A can be negative. A can be real. That's all we know. That's definitely all we know. So -2 times A times X, and we want a slider for A. So this is our function, really. This is our function, how it looks like, right? So it can be negative, right? So it kind of like you see that as we move, and it just does these, right? So this is flex point here at 1. So we know this is definitely 1. And these values won't ever be negative. The values of that, they'll always be between 0 and 1, right? On the z-axis, because I'm assuming x again. I'm assuming x is just one-dimensional here, okay? Which I know I shouldn't, but let's see what we get. So x, so this is, and so now I want to know what is the value of n, so that integral kind of goes to 1. So what we're doing is, and this is just the simple, like again, we assume one-dimensionality. So now what we want to do is we want to basically, so this is 1D. So we take these and we do the so we do we integrate S11 and we integrate on R, and the R is the radius, so this is between 0 and infinite. This is for sure correct. And if we print S12 now, what do we get? For this alpha stuff, I don't really get what is arg A. What is this trying to tell me? The argument complex analysis is the angle between the positive. Oh, but we've told A is real, right? So what the fuck? If we said A is real, why does it even say I don't know, complex. No, the z, the node arc z is the angle between the positive real axis and yeah, so that's the angle. But like, who cares if we know this is real true? Because if we say conditions no, which I'm like, not super happy with these, but it tells me 1 divided by 2 times a. This is the integral of this stuff. For example, if a is 1, or if a is 0, right? I mean, that's the thing, right? So then it's like indefinite. So, but if a is 1, then you have these kind of area here, which is basically, it's telling me that it's what, like 1 divided by 2, 0.5. Let's say whatever. Yeah, okay, kind of. So if it's 2, it's smaller because it's 1/4, right? So if I go to 2, it becomes smaller. At least that makes sense. It grows like this, you know. Okay, cool. And so if I now say, you know, S13 equals, and now I basically say n times conjugate of n times S12, and then we want to basically say solve these minus 1, because solves for 0, and we say print 3. And so it tells me is, you know, for example, square root of 2 times, can we simplify? Say the first solution, right? Whatever it is. So it's square, isn't it like, no, actually it's not. Square root of 2 times square root of a. So for example, if it doesn't matter. Anyway, any of these, but so if, for example, say a is 1, is then square root of 2 times square root of 1 is the component, because then, so if a, or let's say a is 2, then basically I need to have sort of square root of what did I say? Square root of 2. Nah. Square root of 2 times square root of a, which is, can I just move here? Right? I think that's what we're doing, right? Yeah. And then times all these. So that is d. And in theory, that then that is the adjusted. So that's what it has to be. So it's, can I, like, is there a nice one? I don't think that you can do that. I don't think that you can calculate here the integral or something. Functions, statistics. Oh, you can do the integral. So can I just, for example, here do the integral it's got to be definite, so to these, and I guess it's not going to be in infinite here, but we can give it a big number of these things here. What is that? Dx 0.5. It's supposed to be 1, man. It's supposed to be 1, isn't it? We've solved it for so we're doing n times conjugate of n times s12 minus 1 and then solve for n. We've taken the n out. We've just integrated these things. What, so maybe I'm just, you know, it's just too messy, right? But like let's just assume let's do with S1. So we're doing S1 and then we're not, so what we're doing is just S12. So that makes sense. So S1, we integrate S1 and then we solve these. Do I get the same? Should get the same. Yeah, should get the same. Square root of 2 times square root of a. Oh, a. Yeah, a. That's correct. AX. Oh, but I mean, okay, because I have a fixed A, right? Or what? Is it because the other half would make the 1, right? So that's just 1/2. But what am I doing something? What am I doing wrong here? So, because I'm giving A a value. I'm giving A a value and what? I'm not quite getting it. I'm giving A a value. So I'm solving for, so S1 integrated over R 0 to infinite, and then I'm solving for 1, and then I'm printing S13. Now the question is, why is it that I'm getting 2 values? Because of what? What if I just print S12? What S12 looks like? No, yeah, S12 looks like that. And so and what should n be? Yeah, that makes sense. but I don't know why I'm getting there that it's 0.5. If I do a so n is these, right? Oh, sorry, because it's the function is these one, right? So obviously it's kind of like in a way I know I probably can't do the conjugate here, so this is just squared. Exactly, there you go. So now I have 1. Okay, this makes kind of sense in one dimension. So this is one dimension. Cool. How would this look like in 2 dimensions? So now we have x and y. But again, as we said, right, the thing here is you have your z, x, and y axis, and the thing is you have an x and y, but it's still like r is a north, right? So everything that is in the same radius towards this center gets the same z value. So you kind of have, these thing here. Then for these radius, you might have something that looks like this, is a bit lower. So, it's like a 3D kind of maybe cone, I guess, because it's the same thing, right? So you kind of have this, it has the same silhouette, but it's just in kind of, imagine that symmetric around the z-axis. So something like this, right? Awesome drawing skills. So yeah. Now, how do you go about it? So this is definitely no. What is then? This is then already like this. This is not polar coordinates anymore, right? So this is because this is already 3D directly. So this should be, as we said, it should be already, cylindrical, like a sort of cylindrical coordinates integration, which for the 100th time I'm visiting this page, and basically the idea is that polar coordinates, so we want to do this kind of rotational integration thing, right? So, and here's an example with the volume of a sphere, and that's not the shape that we have, but that's kind of as an example. So you want to integrate through the 3 different coordinates, but in this case, you have these r, and again, I'll dive into these, I promise I'll dive into these, but that's just something that, like, the reason why you have this r here is because of how these little sections that you're going to do so really work. As always, the hard part is putting bounds on the integral. However, doing these with cylindrical coordinates is much easier than with Cartesian coordinates. Particularly r and theta will just live within the unit disk, which is very natural to describe in polar coordinates. So you have to, since the bounds of z will depend on the value of r, we'll let the innermost integral handle z, while the outer 2 integrals take care of r and theta. Writing down what we have so far, we get it's important to make sure the order of the differential terms dz, dr, and d theta matches up with the appropriate integral. We know, right? We know that the boundaries are definitely that's the thing, right? If we keep the n here, that's what bothers me a bit. If we keep the n here, the boundaries are definitely not a second. Okay, the boundaries will depend on A, definitely. I mean, yeah, that's definitely n, right? Because it's square root of 2 times square root of 2 is basically, in this case, square root of 2 times, so this is definitely 2, I mean, so this will really be n in this case, right? The function that we're integrating, again, remember, is this is the function that we're integrating. So actually, the z values will depend on n, indeed. But if we were to take n before out of the integral and focus on the smaller sort of unit function and this function that just has a 0 to 1, then kind of it should really work like this. So this is the function that we're integrating, remember. This is n. N is all we're trying to find, but essentially n is really going to be, you know, if I take these and we even have another function that is going to be n times these, and then we add a slider for n, and then we hide these two. Like, no, sorry, we'll leave a to 2. This is really what makes the difference, right? The cross point here is the n. So the z boundary is going to be n. So this tool is part of another which is find the volume of the sphere. For example, you could integrate a 3-variable function, and so that's what we have inside the sphere. And so this is what we're trying to do, basically. Dz, dr, d theta. So, you know, this is the function that we have. And then r. So here you do have to go and say, well, now, you know, let's integrate S1. So we have S1. Let's integrate these times R, and let's first integrate it through like Z between 0 and n. N is still, now there's a question, is it really n or n squared? Because remember, it's n squared, man. The function we're integrating is n squared. The function we're integrating is n squared. Is n squared, yeah. Remember. Well, it's you know, that's the trick, right? It is n times its conjugate. That's what's complicated. That's what's complicated, because it could be a complex number, although we know it isn't, but I don't know why we can figure out that it isn't. But it's really n squared is the top, because that's the function that we're integrating, is this one. Really, is the probability density function. Then we solve these, and then we print these, right? So this is 1D. Yeah, okay, sorry, but that's not the whole thing. So that's just, we first integrated it over Z. Then we need to integrate it, over R. And then we need to integrate it over theta. And so theta is going to be this B thing here. So B, and this is 2 pi, because we want to give the full circle. And once this is done, then we're going to solve by 1 and print it. Why the fuck am I getting different results than I was getting last time? Oh, yeah. What if I just do these to be more correct? Then we have 4 options. Which again is kind of fine, right? Because I still have the feeling that we're talking yet one more dimension, right? This is kind of like for 2 dimensions. You know, which I can't, because I don't know how can I do polar stuff in here, but probably I can. But if I, you know, yeah, essentially I'm assuming that is the thing, right? So first Z, like Z goes, is the problem is fucking complex numbers. That's the fucking problem, man. What the real true? Wait. Why the fuck do we have complex answers now? I don't get these. Am I missing some notation somewhere? What am I doing? So integrate over Z, 0 to n squared, then over R, 0 to infinite, and then over theta, 0 to 2 pi, and then solve. Why am I getting complex answers when I know that n is real? What the heck? Like, how can this be? Huh? S1. We're taking these. Yeah. N is real. Have I saved this? Do I have to? Oh. But that's different than what I was getting before. That's different than what I was getting before. Even like before, like when I was doing this like that. Maybe I should use, maybe the variable reusability here is like, you know, S13, and so S13 should be S14, and so can we just get rid of these, and can we just call these things like S1? No, S2 is this one, and then S2, and this is S3, and then you print S3, and here's like S2, then you get S2 and becomes S3, then you get S3 and becomes S4, and then you solve with S4, and then you have S5, and then you print S5. Does this change anything? No, of course it shouldn't, right? But at least it's clear. But that's different than I was getting before, so I have no idea. Now I'm even more lost. We know R is real and positive. We know A is real. Oh, maybe it's because I before used to have these. Could it be? That's why I was getting different things. Ah, could be. Could be. We know A is real. It doesn't have to be necessarily positive. And well, and in, you know, and in theory doesn't have to be. I just don't know, for the love of, like, for the sake of God, how would anyone do that by hand? Like I without assuming certain things. It's just insane that if I don't assume anything about n, that now, like, I don't have any complex answers, whereas when I assume, yeah, it's different n squared than n times conjugate, right? The problem is that if n can be complex, then that just goes to hell. Like, my analysis here doesn't necessarily work, so I probably have to really just take it out of the integral and work with 0, 1. I think that's what makes most sense. You know, like I have, so let's say you take n squared out of the so you start off with this function. Let me rewrite these. Okay, so S1 essentially, because I can S1 is basically n times conjugate of n times, and then I have these exp minus 2 times r, right? So this is my S1, or let's say S0. But S1, for these, we can just take these things out of the integral. Like, you know, we all we care is, you know, we want to work just with these because it's a simpler integral to deal with. It's a simple integral to deal with. Then we know that the z goes from 0 to 1. right? Because there's no complex numbers here. We know A is real. There's no complex numbers. We can make the analysis on the assumptions. So we work with 0 and 1 as in the Z integral part. 0 and 1. Then we do the R integral part, so from 0 to infinite. Then we do the theta part from 0 to 2 pi. And then what we do is we bring in this part here and say cool now, because we don't know anything about n. So now we say S4 times these, because remember the integral of a constant times the function is the same like the constant times the integral of the function. So this is the integral of the function. And so now we do this stuff, we do -1 and solve for n. And then and now we see what happens. Okay. This is looking better, I have the feeling. Yeah, I have the feeling that's looking a bit better. Now, how do we take that to like 3D? First of all, does 2D make sense still? If we do the same concept for 1D. So we just, you know, to be honest here, it's like you're just integrating on this thing R 0 to infinite, and then not these, not that. So you're saying S2 is the integral from 0 to infinite for from dr, and then at the end you're saying take that at these, solve for n. This is basically S3 and print S3. And if we do that, what do we get? We should be getting the same thing. Yeah, okay, cool. We get the same answer. That's good news. That's good news. That's good news. That's good news. Let me just get rid of this. It's all confusing and noise. So that's 2D. Okay, cool. We keep that. So now 3D. How do we go 3D? Like in 3, you know, that's the problem is here we have a fucking 4th dimension. So we have a 3D point. I just can't visualize that. That's the problem. I mean, I think that still holds. Z is still always between 0 and 1. Radius is always between 0 and infinite. Now it's just more about the 2 pi thing and whether we don't have to introduce a sort of another symbol here, that it's maybe going to be B2 or theta 2, and kind of have another, like this is what I would just intuitively think, and this is B2, but you know, I have no idea. And this is probably where I have to, so far just I think it makes sense, the what I'm doing. So the boundaries are simple. It seems pretty simple, and it's just, you know, I don't know whether that's what you do in the 3D, in the 4D case. 3D space. Okay, let's be clear. 3D space, this is 2D space, this is 1D space. So we do that. Also, let's say just, you know, 2 pi, because we're just doing the whole the full circle. And then we take S5 and add these things and solve for 1. And then we print S6. Let's see what happens. Divided by pi. Fuck you, man. Fuck you. A divided by pi. The solution is indeed an a divided by pi, but it's a to the power of 3 divided by pi, and then it's the square. It's to the power of 3. Yes, because this is not correct anymore. Well, and that's not correct anymore. No, that is okay. That's what I'm missing, because this is for cylindrical coordinates. So what about like an n-dimensional cylindrical coordinates? This is what we want. Boom, bim, bidi, bim, boom, boom. An n-dimensional cylindrical coordinates. Full circle, cylindrical. I have to write all these, read all these. High dimensions. For spherical coordinates, there is a well-defined generalization to n dimensions. So maybe we just have to move to spherical coordinates. Exactly. That's probably what we have to do. And this is what I was trying to do. Spherical coordinates, interdimensional spherical coordinates. Exactly. This is what I'm looking for. Yeah. This was these exactly. So I need to add these angles, and it's like sinus, right? So it's r to the n minus 1 times sinus. So the integral, so here it's in theory r to the n minus 1, which is r to the I guess it's this, because it's n is 3. No, is it? No, n is the dimensions, which is we're 4-dimensional, so it's 3. So r to the power of 3 times sinus of the, theta, right? So this is b sinus, okay, sinus to the power of n minus 2, so square. And then times sinus of theta 2. I think that's the thing. That's what you're doing. Sinus of theta 2, because it's like n minus 3. It's like 4 minus 3 is 1. Cool. And so I mean that's already we're here. Essentially goes until like theta 2, right? Because it's theta 3. No, I think that's correct. 1, 2, okay. I think that is correct. And so I think the order is also correct. And so first we're integrating over z, then we're integrating over r, then we're integrating over theta, and then we're integrating over theta 2. I think that is the difference. Awesome. And I think we're going to leave it here, but I think that is the, I mean, let me see. If I, or let's try to spherical integration. So let's see if we can do the spherical integration of these, which actually was r, it's basically r squared times sinus of theta, right? Oh, but wait a second. I think then it's a bit different. The result is a bit different. So we're doing, yeah, exactly. But then you do dr and then, so there are two angles here already. Sorry. I just want to compare, make sure I get the same results. So it's not z in this case. So we have already two angles. And so first is r 0 to infinite. Then it's b 0 to 2 pi. And then it's b2 0 to 2 pi. So this is what we're doing exactly, I think. Empty as well. Don't like it. Don't like it. So S2 is S1 times r squared sinus of theta, and then we're integrating these 0 to infinite. Then we're doing S2 theta 0 to 2 pi. Oh yeah, because here we're saying that for some reason I was like yeah, this is pi because we know there's no negative results. Exactly. I think that was the point. And I think what I was getting here, also nothing. Fuck. Crap. S4. 0. That's the problem. 0 to pi. Am I doing this in the right order? R, then this guy. I think I'm doing it the other way around. I think I might be doing it the other way around. I think I might be doing first B2 0 to pi, and then B 0 to pi. I think I might be doing it the other way around. I like it. I like these. I like these because there's an alpha to the power of 3. Oh. It's still backwards though, but I have an alpha to the power of 3. But I don't like it because it doesn't give me the same result like this one, and it should, you know. That's the problem. They both should give me the same result. So first need to get that right. Yeah, that's definitely something off here. What if, I mean, if I do 2 pi, I'm gonna get the same, right? That doesn't matter what order I put the variables, that's just the same shit. 0. Okay, need to work. Okay, but I'm on the right path. So 2D space spherical integration, because when we go to 3D space, it's basically I don't know. The thing is, it just feels overcomplicated for what it is, you know, people. It's this fucking exercise here. Like, is that complicated? Is that fucking complicated? That's supposed to be an easy integral. So why am I? Yeah, but I mean, in theory, you know, in theory it is, right? It's just not a complicated thing to do by hand either, I think. R squared sinus of theta 2, maybe that's the thing, right? Or not, or what? Yeah, that's the other angle. So that's an important aspect of it. Still get the same. Still get the same. First angle, the first angle, and the second angle. So it's the same, like if I do these, right? I guess that's just going to be the same thing. Okay, I have to dive into this. I have to go now, but I think that is not looking bad at all. I just need to make sure that I get the same results, because this bothers me. I should get the same results, and this is not, definitely not the same results. This seems to be an easier approach though. Why isn't it giving me the same? So, r squared. R squared. Oh, we're doing the angles first. Okay, and then r at the end. Maybe that's the reason. Is that so? Here you're doing first r. What the fuck? Why? Well, it doesn't matter, right? As long as you match the boundaries, I think it doesn't matter which one you integrate first. Right? As long as you match the boundaries, it's just okay. Like this is r, 0 to infinite, and then the one angle is pi, another one is 2 pi. I thought this was the right order, but apparently it is not, because that gives me 0. Anyway, we're getting closer somehow, people. Not bad, not bad. Oh, bye bye.